OceanGate expeditions aim to democratize deep-sea exploration. The Titanic wreck served as a primary attraction for OceanGate's deep-sea expeditions. Democratizing deep-sea exploration involves making it accessible to a broader audience. Submersible tourism enables civilians to explore ocean depths formerly accessible only for scientific or military purposes. Submersible tourism expands access to underwater environments, offering unique experiences to a broader audience. Submersible tourism provides opportunities to observe marine ecosystems and geological formations in their natural state. Stockton Rush's vision centered on democratizing deep-sea exploration. Rush aimed to make deep-sea expeditions accessible to a wider range of individuals. The ambition to create the Titan submersible was driven by the goal of broader participation in underwater exploration. Carbon fiber was selected for the Titan's hull due to its high strength-to-weight ratio. The use of carbon fiber in deep-sea submersible hulls was controversial due to a lack of established performance data. The Titan's carbon fiber hull represented an unproven application of the material in extreme deep-sea conditions. The submersible design incorporates off-the-shelf components to minimize development costs and time. Using standard parts raises concerns about integration and compatibility within the submersible's complex system. The reliability of off-the-shelf components is questioned under the extreme pressure and corrosive conditions of deep-sea environments. The Titan submersible lacks certification from any recognized maritime safety organization. Absence of certification means the Titan did not undergo independent testing and validation. Independent testing and validation are crucial for ensuring the safety and reliability of submersibles. Engineers raised concerns regarding the Titan's design and safety protocols. Risks were identified with the carbon fiber hull and experimental features of the submersible. Potential hazards associated with the Titan's design were highlighted by experts. On June 18, 2023, the Titan submersible commenced its final descent toward the Titanic wreckage. The submersible carried a crew of 5 passengers during this descent. This descent marked the beginning of the Titan's mission to explore the Titanic wreckage. Communication between the submersible Titan and its support vessel, the Polar Prince, was lost approximately 1 hour and 45 minutes into the dive. The loss of communication occurred during the submersible's descent to the Titanic wreckage site. This communication failure initiated subsequent search and rescue operations. Following the loss of communication, a large-scale international search and rescue operation was launched. This operation involved the coordinated efforts of multiple agencies across different countries. The search and rescue operation was initiated in response to a communication breakdown. At the depth of the Titanic wreck, the pressure is approximately 400 times greater than at sea level. This immense pressure exerts significant force on any submerged structure. The extreme deep sea pressure is due to the weight of the water column above. An implosion occurs when external pressure exceeds the internal pressure of an object. The structural integrity of a vessel is crucial in resisting implosion. When external pressure overcomes internal resistance, the vessel collapses inward rapidly. Carbon fiber materials are susceptible to fatigue under repeated stress cycles. High-pressure cycles can lead to delamination within the carbon fiber structure. Fatigue and delamination can weaken the overall structural integrity of carbon fiber components over time. The Titan lacked a comprehensive acoustic monitoring system. Acoustic monitoring systems are designed to detect hull stress in real time. Without acoustic monitoring, potential hull failure points could not be detected. The Titan submersible utilized a fundamental text-based communication system. This communication method restricted real-time data transmission capabilities. Limited communication hindered effective emergency response capabilities. Navigating in extreme depths requires reliance on sonar technology due to limited visibility. External cameras provide a visual feed, compensating for the lack of direct observation. The submersible's navigation system integrates sonar data and camera feeds for spatial awareness. Confinement in a small cylindrical space restricts passenger movement. Prolonged missions in confined spaces present significant challenges for passengers. Limited movement within a confined space can impact passenger well-being. The allure of witnessing the Titanic wreck firsthand motivated passengers to embark on the submersible journey. Passengers accepted the inherent risks associated with the experimental submersible technology. The desire to see the Titanic wreck firsthand outweighed the perceived dangers of the deep-sea exploration. The search and rescue operation for the missing submersible involved resources from multiple countries. International collaboration reflected global concern for the missing submersible and its crew. The coordinated effort aimed to locate and potentially rescue the submersible using diverse resources. Underwater acoustic sensors were deployed to detect potential signals from the Titan submersible. The sensors were designed to listen for distress calls or implosion sounds. Analyzing acoustic data is crucial for locating the submersible in deep-sea search operations. The estimated 96-hour oxygen supply became a critical constraint in the search efforts. This limited oxygen supply created a race against time to locate and rescue the passengers. Effective search and rescue operations were essential to maximize the chances of survival within the given time frame. The Titan's experimental design raised significant safety concerns. The lack of formal certification for the Titan was a critical oversight. Experts identified potential risks associated with the Titan's unproven technology from the outset. Carbon fiber was selected for the hull material. The selection of carbon fiber was innovative but lacked sufficient testing for deep-sea conditions. Insufficient validation raised concerns about the long-term reliability of carbon fiber in deep-sea applications. The absence of standard safety protocols increased the risks associated with the Titan's dives. The lack of redundant systems further exacerbated the potential dangers during the submersible's operation. Insufficient safety measures compounded the overall risk profile of the Titan's deep-sea explorations. Remotely operated vehicles (ROVs) identified a debris field. The debris field confirms the catastrophic implosion of the Titan submersible. The debris was located near the wreck of the Titanic. The implosion resulted from the structural failure of the carbon fiber hull. Extreme pressure caused the hull to collapse instantaneously. The structural failure led to an instantaneous implosion. Multiple agencies initiated investigations to ascertain the precise cause of the implosion. These investigations aim to evaluate the regulatory oversight governing submersible operations. The goal is to identify potential safety gaps and prevent similar incidents in the future. The disaster led to heightened examination of the regulatory framework for deep-sea submersibles. Increased scrutiny focused on the safety standards governing deep-sea submersible expeditions. The regulatory framework's effectiveness in ensuring the safety of deep-sea expeditions was questioned. The incident highlights the ethical considerations surrounding innovation and experimental ventures. Balancing the potential benefits of innovation with the safety of participants is a crucial ethical challenge. Risk assessment is essential to ensure passenger safety in experimental projects. The degree to which passengers were fully informed about the risks associated with the Titan submersible's dives is under scrutiny. Ethical considerations surrounding informed consent are central to the investigation. The debate focuses on whether passengers truly understood the potential dangers involved. Cylindrical hull designs are simpler to manufacture compared to spherical designs. Cylindrical hulls may be less optimal for withstanding extreme pressure. Spherical hull designs offer greater structural integrity under extreme pressure conditions. Submersible end caps are critical components that seal the hull, preventing water ingress. Stress concentrations at the end caps can lead to structural failure and potential leaks. Proper design and material selection are crucial to ensure the end caps can withstand extreme pressure. The absence of real-time monitoring for hull stress hindered early detection of potential issues during the dive. Without continuous hull integrity assessment, critical structural weaknesses may go unnoticed. Real-time monitoring systems are essential for proactively identifying and mitigating risks to hull integrity. The Titan's emergency ascent system was reportedly unreliable. An unreliable emergency ascent system reduced the chances of a successful recovery in case of a problem. The compromised emergency ascent system posed a significant safety risk. The Titan submersible had successfully completed multiple dives to the Titanic wreckage before its final voyage. These prior successful dives may have contributed to a misleading sense of safety and reliability. The accumulation of successful dives did not guarantee the structural integrity or safety of future expeditions. Questions arose regarding the Titan's maintenance records. The integrity of inspection and repair procedures following each dive was under scrutiny. The adequacy of post-dive maintenance directly impacts submersible safety and operational reliability. Extreme pressure at depth can cause significant compression of materials. Material compression can alter the physical properties of substances. Compression-induced changes can affect the structural integrity of materials. Rapid compression during an implosion generates intense heat. The heat generated by compression significantly contributes to catastrophic destruction. Implosion-induced heat exacerbates material failure and structural collapse. Carbon fiber is susceptible to delamination, a separation of material layers. Delamination weakens the overall structure of carbon fiber composites. Delamination increases the risk of structural failure in carbon fiber materials. Carbon fiber hulls are susceptible to damage from impacts and collisions. Impacts can compromise the structural integrity of the submersible. Debris on the ocean floor poses a collision risk to deep-sea submersibles. A single point of failure in communication systems can lead to a complete loss of contact. Redundant communication systems are necessary to maintain contact in the event of a primary system failure. The absence of backup communication systems can result in severed contact during critical operations. Environmental conditions can affect sonar systems, limiting accuracy in deep-sea navigation. Interference from marine life and other vessels can reduce the effectiveness of sonar signals. Deep-sea navigation using sonar is susceptible to signal distortion caused by temperature and salinity gradients. The confined space of a submersible can induce psychological stress. Darkness and isolation during prolonged dives can exacerbate psychological effects. Prolonged exposure to these conditions may lead to increased anxiety and disorientation. Passenger training on emergency procedures is a critical aspect of aviation safety. Comprehensive safety protocols ensure passengers are well informed and prepared for potential emergencies. The effectiveness of passenger training is directly related to preparedness and survival rates during emergencies. Remotely operated vehicles (ROVs) were deployed to aid in the search efforts. ROVs utilized sonar technology to scan the ocean floor for the missing submersible. Cameras mounted on the ROVs provided visual confirmation during the underwater search. Debris field analysis provides insights into the nature of an implosion. The analysis reveals the magnitude and direction of forces involved during the implosion event. Information extracted from debris helps reconstruct the sequence of events leading to the implosion. Decreasing oxygen levels inside the submersible would lead to a corresponding increase in carbon dioxide. Elevated carbon dioxide levels can cause discomfort and impair cognitive functions. The balance between oxygen supply and carbon dioxide removal is crucial for maintaining a safe environment within a closed system. Experts advocate for enhanced regulatory oversight of deep-sea submersible operations. Stronger oversight aims to prevent future tragedies related to deep-sea submersible activities. Regulatory improvements are crucial for ensuring the safety and reliability of deep-sea submersible operations. Rigorous testing standards are essential for ensuring the safety of submersibles. Comprehensive testing of submersible components is crucial for reliability. Enhanced testing protocols minimize potential risks associated with submersible operation. Implosion involves a rapid, inward collapse. The implosion event occurs in a fraction of a second. Implosion results in the instantaneous and complete destruction of the submersible. The disaster involving OceanGate raises potential legal implications for the company and its executives. Legal liabilities may include charges of negligence, indicating a failure to exercise reasonable care. Wrongful death claims could be filed, alleging that the company's actions or omissions led to fatalities. The incident significantly impacted the submersible industry. Increased scrutiny and re-evaluation of safety practices resulted from the event. The submersible industry faces a period of reform and renewed safety standards. Commercial pressures in deep-sea exploration can lead to compromised safety standards. The drive for commercialization may incentivize overlooking critical safety protocols. Prioritizing profits over safety can result in cutting corners during deep-sea operations. The disaster significantly impacted public perception regarding the safety of deep-sea tourism. Public perception of deep-sea tourism now includes increased awareness of potential risks and ethical concerns. The event underscored the need for stringent safety measures and ethical guidelines in deep-sea tourism ventures. Pressure testing simulates deep-sea conditions to assess structural integrity. The extent of pressure testing is crucial for evaluating the Titan's ability to withstand extreme underwater pressures. Comprehensive pressure testing is essential to identify potential weaknesses and ensure safety in deep-sea environments. The manufacturing process of the carbon fiber hull involves meticulous steps to ensure structural integrity. Quality control measures are implemented throughout the carbon fiber hull manufacturing process to identify potential flaws. Examination of the carbon fiber hull manufacturing process aims to prevent defects and ensure high-quality output. The absence of redundant systems for critical functions increases vulnerability. Communication and emergency ascent are critical functions requiring redundant backups. Redundancy ensures operational continuity and safety in the event of primary system failure. The lack of independent verification for the Titan's design and safety protocols sparked concerns regarding the company's self-regulatory practices. Independent verification ensures unbiased assessment and adherence to established safety standards. Self-regulation without external oversight can lead to potential conflicts of interest and compromise safety measures. Weather conditions at the surface impact submersible operations. Submersible operations are also affected by weather conditions at depth. Weather conditions influence the effectiveness of search and rescue efforts involving submersibles. Emergency procedures for the Titan were examined to determine their effectiveness. The adequacy of the crew's emergency training was a key area of investigation. Scrutiny focused on whether the procedures and training sufficiently prepared the crew for potential emergencies. Buoyancy control is essential for submersible operations. Failure in the buoyancy control system can lead to a loss of control. Precise buoyancy adjustments are critical for maintaining depth and stability. Extreme cold at depth can significantly alter the properties of materials. Electronic systems may experience performance degradation or failure due to low temperatures. Material contraction and changes in conductivity are common effects of extreme cold. Submersible materials must withstand corrosion in harsh marine environments for long-term reliability. Corrosion resistance ensures the submersible's structural integrity and operational safety. Material selection is critical for maintaining submersible performance and longevity. Sealing technology is critical for preventing water ingress in submersibles under extreme pressure. Effective sealing ensures the safety and operational integrity of submersibles in deep-sea environments. Advanced sealing materials and designs are essential for withstanding immense hydrostatic forces. Underwater communication systems primarily utilize acoustic signals for transmitting information. Acoustic signals in underwater communication are susceptible to noise interference. Noise and interference can significantly affect the reliability of underwater communication. Global Positioning System (GPS) signals are unable to penetrate water. Submersibles must use alternative navigation methods due to GPS limitations. Sonar and inertial navigation systems (INS) are common alternatives for underwater navigation. The confined space within a vehicle can contribute to motion sickness in passengers. Limited visibility exacerbates motion sickness by disrupting the balance between visual and vestibular input. Motion sickness arises from a sensory mismatch between what the eyes perceive and what the inner ear senses. The presence of emergency equipment is a crucial factor for passenger safety. Oxygen masks are essential emergency equipment for maintaining passenger safety during flight. Survival gear contributes to the overall safety and well-being of passengers during unforeseen events. Surface vessels coordinated search efforts by strategically positioning themselves across the search area. These vessels served as platforms for deploying and managing underwater vehicles during the search operation. Surface vessels facilitated real-time communication and data relay between underwater vehicles and command centers. Sonar data analysis played a crucial role in identifying the location of the debris field. Camera sensor data was essential for understanding the nature and distribution of the debris. Comprehensive sensor data analysis was critical for determining the cause of the implosion event. Oxygen consumption within a submersible is directly related to the number of occupants. Occupant activity levels significantly influence the rate of oxygen consumption. Monitoring oxygen consumption is crucial for maintaining a safe and sustainable environment inside the submersible. The disaster underscores the critical importance of prioritizing safety in all deep-sea exploration activities. Effective regulation and oversight are essential to prevent future incidents during deep-sea operations. Ethical considerations must guide deep-sea exploration to ensure responsible and sustainable practices. Future submersible development will likely include more stringent safety standards. Advanced materials will play a key role in the next generation of submersibles. Improved monitoring systems will enhance submersible operational awareness and safety. An implosion generates a powerful pressure wave. The pressure wave propagates rapidly through the surrounding water. This pressure wave can potentially affect nearby structures and marine life. Memorials serve as places of remembrance and honor for those who perished in the Titan submersible disaster. These memorials provide a space for collective mourning and reflection on the tragic event. The memorials stand as a lasting tribute to the lives lost and a reminder of the risks involved in deep-sea exploration.